All right, everybody. We have finished talking about the ionic compounds, and we're going to chat about covalent bonds, the molecular compounds today. We're going to talk how to name them. Okay. And we're going to start with basically the definition of the molecular compound. Molecular compounds are formed by non-metallic atoms like chlorine or fluorine or hydrogen or carbon. And the most important thing for us to determine in any molecular compound is how many bonds this non-metal forms when it interacts with other atoms. And usually the number of bonds in most cases is determined by the number of electrons the non-metal needs to achieve a stable electron arrangement. Before we move forward, a simple question. What is the stable electron arrangement for the outer shell? How many electrons? 8. So, let's say we have a carbon atom, which has 4 electrons on the outer shell. How many more electrons does it need to have? 4. That's how many bonds it's going to form. Does that make sense? Bonds, chemical bonds. So, the main difference between the molecular compounds and ionic compounds is that in molecular compounds, we see mostly nonmetals that share electrons. Remember, when we talked about ionic compounds, we considered electrons being moved from one atom to another, so they form positively and negatively charged ions. In molecular compounds, electrons are shared, forming covalent bond. And the electrons that are shared are valence electrons. Okay, the electrons on the outer shell. It doesn't have to be 2 atoms. In compounds that we are familiar with, like molecule of hydrogen, H2, there are only 2 atoms. But in the water, there are 3. In the molecule of methane, which formula is CH4, there are 4 atoms. And if you think about large organic molecules, that can be dozens of atoms. Does that make sense? Okay. So let's take, as an example, a process of formation of hydrogen molecule. So atoms of hydrogen move closer and closer together. Remember that nuclei of hydrogen atoms are positively charged. So they start to attract electrons of the opposite, other atom. So here you have positively charged nucleus. Here you have negatively charged electron. Here is another positively charged nucleus and negatively charged electron. This electron gets attracted to this nucleus. This electron gets attracted to this nucleus as these atoms are moving together, okay, closer. At some point, these electrons become close enough to start basically belonging to both nuclei. So this nucleus on the left, on the right to you, nucleus on the right, quote-unquote, considers this electron its electrons, and nucleus on the left starts to consider these electrons its own. So they are shared. Does that make sense? And when this nucleus has two electrons on the first electron shell, first electron level, corresponds to which element, to electron configuration of which element? Two electrons. Anyone has periodic table close? So which element has only one electron shell and two electrons on it? Helium. And it's a perfect arrangement. Helium is a noble gas. Does that make sense? And when this perfect arrangement is achieved, this molecule, the molecule of that consists of two hydrogen atoms, is more stable than two individual hydrogen atoms. So far, good? So here this process is illustrated on the graph where distance between nuclei is plotted on the x-axis and the energy of the system, the whole system, is plotted on the y-axis. So you can see that the total energy of two separate hydrogen atoms is higher than energy of hydrogen molecule. And it's basic law of nature that you can observe in many systems. Every system attempts to lower its energy. Does that make sense? The very simple example of it, which human body position is more stable? Standing or lying down?
Lying down.
Lying down. And when you lie down, your potential energy is lower.
Wow.
Does that make sense?
Yeah.
This is why it's more stable. So, in order to demonstrate how electrons are shared in the molecular compounds with covalent bonds, we use so-called electron dot formulas. These electron dot formulas demonstrate how many electrons are on the outer shell of each atom and which electrons are actually shared. For instance, if we try to draw the electron dot formula for fluorine, we need to draw two fluorine atoms first. Fluorine is the element found in the 7th representative group. If you have, by this time probably know, but it's in the 7th group. So how many electrons are on the outer shell?
7.
7. So here you can see, if you count, there are 7 dots. Each dot represents one valence electron. 7 dots here. Okay? So how many electrons does each fluorine need to achieve the octet? Just one, to achieve the perfect configuration. So each fluorine will, quote unquote, donate one electron, and they will form that bond. Okay, I cross it here. Okay, does that make sense? Mm-hmm. Now, what's going to happen to other electrons? 6 other electrons that do not participate in the bond formation in this particular example will form lone pairs. It's an official term. So in a molecule of fluorine, there is one bonding pair and 3 lone pairs per atom. Can you see that? So each of these pairs that do not participate in the bond formation, by definition, is called a lone pair. Alone, Now, You may have noticed that we picked two molecules that are formed by the same atoms. Hydrogen, H2, and fluorine, F2. Do all nonmetals form such molecules? The answer is not. So these are the elements that form such molecules. Only 7 diatomic molecules. Before the class started, I was actually sitting in the hallway preparing the study guide for this unit. It's almost done. And these are 7 diatomic molecules that you should know. Okay, I will ask this on the exam. Okay, so hydrogen, nitrogen, oxygen, and all halogens. Fluorine, chlorine, bromine, and iodine. That's it. That make sense? That's just memorizing. Now, this statement here, when you read it, it's really confusing. So this is why I always say chemistry is very, visual science. So think about this. If you have a hypothetical chemical element which has 5 electrons on the outer shell, it's non-metal of some sort. How many electrons does it need to achieve a perfect configuration? 3. How many electrons does it have to share to achieve the perfect configuration? 3, right? It gives its own 3, and some other atoms will give their own 3, so they will share, okay? There will be a total of 8. So how many shared pairs will this form? 3 shared pairs, meaning 3 covalent bonds. So say nitrogen and phosphorus, elements of the 5th group, they can both form 3 bonds. The example is the compound known as ammonia, NH3. Have you ever smelled it? Okay, you know what it smells like. For phosphorus, it's going to be phosphine, PH3. I can bet no one ever smelled it. Because if you would, you'd be dead. It's very toxic. Okay? For oxygen, it's going to be 2 bonds. You can see it in an example like H2O. Does that make sense? For chlorine, it's going to be 1 bond. You can see it in the example like HCl, where it forms 1 bond with a hydrogen. Does that make sense? We're good? Understood? Okay. So what if you're dealing with the molecule that consists of 2 different types of atoms, and it's more than 2 atoms, like the molecule of methane? Okay, so you know that there is carbon, you know that there is hydrogen. Are you following me? Mm-hmm. So that's the electron configuration of the outer shell of the carbon atom, 4 electrons. This is hydrogen, 1 electron. So what you do? Hydrogen has only 1 electron to share. Carbon has 4. Now, one thing to remember, which is really important. We talked a lot about how elements, how nonmetals wants to achieve the 8 electron configuration on the outer shell, so-called octet. Right? We just mentioned it. There is an exception. It's hydrogen. Can you tell me why hydrogen doesn't need 8 electrons? How many electrons can be on the first layer? Only 2. That's it. That's the answer. That's the maximum. That's the most stable, the only stable number on the first. So hydrogen needs only 2 electrons to achieve the stable electron configuration. Does that make sense? I'm sorry. Sorry that I didn't turn off the sound. Okay? We got it? So those are electron dot formulas for some common molecules. And I want to sort of repeat some of them. And we will already did methane, so let's do ammonia. Nitrogen, how many electrons on the outer shell?
5.
5. If you don't mind, it's really hard to draw a dot with my pen, so I'm going to do little strikes here. Okay, 5. How many electrons does nitrogen need to share to achieve the perfect configuration? 3. So how many electrons does each hydrogen have to share?
1.
1. So how many hydrogens do you need to deliver 3 electrons? 3. So you have, how many bonding pairs you need? Let's count. You have 1, 2, 3. How many lone pairs? Just 1. Does that make sense? You got it? Good. Let's talk about water. Let me erase it. Let's talk about water. So oxygen. How many electrons on the outer shell? 2. No. No. How many electrons? 6. Okay, 1, 2, 3, 4, 5, and 6. Okay? So, how many electrons does it need to share to achieve the perfect configuration? 2. How many hydrogens you need?
2.
Bingo. How many lone pairs? 2. Perfect. That makes sense so far? We're good?
Yeah.
So, octet rule is useful, and it's really useful. But just like in English language, the exceptions are the important part of this rule. Phosphorus, sulfur, and 3 halogens, chlorine, bromine, and iodine, can form the compounds in which they have 10 or 12 valence electrons. Okay? My memory serves me well. Phosphorus pentachloride has 10 electrons. 10 bonding electrons. That makes sense? So each chlorine has, I think, 10. And sulfur may have 12 in a compound like sulfur hexafluoride. Those are exceptions. We may address them, but my goal on the exam is to ask you the rule rather than exception. Does that make sense? So don't be afraid. Don't think, oh, he's going to throw a curveball. No, I will not throw a curveball. If you can do an octet, that's all I want. Am I clear?
Mm-hmm.
Now, what if you have 2 atoms that share 2 atoms that share 2 pairs of electrons? This forms a double bond. Here's the example. Remind me, please, how many electrons, does oxygen have on its outer shell?
6.
1, 2, 3, 4, 5, 6. Obviously, another one is going to have 1, 2, 3, 4, 5, and 6. That makes sense?
Mm-hmm.
So, if you will take 2 oxygens, they can share this pair. And sorry, I just don't have space. This pair. So you have 2 bonding pairs, which form a double bond. You have 2 lone pairs. And how many electrons in this molecule does every atom, quote unquote, own? What's the configuration for this oxygen, for instance? How many electrons on the outer shell for this oxygen?
6.
After molecule is formed? 8. 2 lone pairs and 2 shared pairs, because it shares the pair with another one. Does that make sense?
Mm-hmm.
It shared pair kind of belongs to both atoms simultaneously. Does that make sense? So, how do you draw an electron dot formula of a molecule? And remember, we're going to focus on the octet. Okay? Well, first, you need to figure out the arrangement. You have to position them. Okay? Basically, you need to just find the central atom and draw the lines to all others. So, for instance, in the molecule of water, what's going to be kind of a central atom? Oxygen. And hydrogens will be kind of like this, right? In the molecule of methane, which is CH4, what's going to be the central atom? Carbon. So hydrogens will be positioned something like this. Right? That makes sense? That's the first thing that you need to do. Second, you determine the total number of valence electrons. Total. Like for everything. Then you need to give 2 electrons per bond. Right? Because you need 1 pair for each bond. And then you have a certain number of electrons left. You distribute them between the atoms to make an octet. Remembering about hydrogen. So to make this more sort of tangible, let's draw this formula for the molecule of carbon dioxide. So the central atom in that molecule will be carbon, right? Usually, kind of a general rule, the central atom is the first. Like CO2, C is the first, okay? SO2, S is the first. Okay, we got it? So that's the arrangement.
So O, you mean O always at last?
No, well,
CO2
hold on, say it again,
has
say it
O.
again, say it again.
So the O always,
Essentially, how it's written, the first element.
The first element, the last element is most non-metallic.
Right.
So if you take sulfur and oxygen, oxygen is more non-metallic than sulfur. Does that make sense? There is one exception to that rule. Which element is even more non-metallic than oxygen? Huh? Noble gases are just boring. They don't react. I mean, the elements that actually do
Fluorine.
fluorine. There is a compound in which oxygen goes first. No,
Oh,
it's this. Oxygen hexafluoride. It's insanely unstable, but it can be produced. Because in this case, fluorine is even more non-metallic than oxygen. Obviously, it's out of our scope of interest, okay? So far, we good?
okay.
Next, so we determine the arrangement. Next, we determine how many valence electrons we have in total. Carbon, 4. Each oxygen, 6. 6 plus 6 plus 4 gives us 16. So that's total number of electrons in that molecule. I'm talking about valence electrons, of course. Got it? How many bonds do we need? At least in the arrangement like this. Sorry, that's oxygen, obviously. How many bonds there are? At least 2. So we immediately have to take 4 electrons for sharing. Does that make sense? Okay. So we take 4 electrons and 2, 2. How many electrons do we have left? 12. Now we need to distribute these 12 electrons between these atoms to achieve the octet rule. So let's say we do this. 1, 2, 3, 4, 5, 6. Nothing here. 1, 2, 3, 4, 5, 6. In this case, and remember, each of these bonds is 2 electrons. In this example, the one that I show you here, oxygen, does it have octet? Let me redraw it more appropriately. Yes, it does, but I'll still. My artistic capabilities are terrible, but I will try to do a little bit better job here. So that's the C in the center. It's one oxygen. This is another oxygen. So here they share a pair, right? That's another pair. And in my example, oxygen takes the rest. Does oxygen have octet?
Yes.
Both of them, right? Carbon, does it have octet?
Yes. No.
No. How many electrons does it have?
4.
Only 4. So what we can do, we can take 2 electrons from each oxygen, right? And move it to make a bonding pair. Essentially doing this. Now, oxygen, does it have octet?
No.
Hold on.
Yeah.
Yeah.
1,
Yeah.
2, 3, and 4, right? It does.
Yeah.
Carbon, does it have octet?
It does now. Yeah.
No.
It does now. How many bonding pairs?
4.
4. So 1 bond, another bond, 3rd bond, and 4th bond. So carbon has 2 double bonds that connected to 2 oxygen atoms. Does that make sense? How many lone pairs? Total?
2.
4.
Oh.
1, 2, 3, and 4. For the whole molecule. That make sense?
So do we just rearrange oxygen's electrons? Is that all that happened?
You do it. Like you rearrange it.
Okay.
Well, it's not. You rearrange it to make an actual molecule, because an actual molecule has the arrangement like this. But you always have to think, how can we make an octet? How can we make a molecule more stable?
Okay.
Does that make sense?
Yeah.
And that will be the most stable arrangement. That make sense?
Yeah.
So some molecules can have even triple bonds. Like here. Okay, the molecule of nitrogen has a triple bond. That makes sense? We can try and draw a molecule that will have another triple bond. A molecule of acetylene. Have you heard about the gas named acetylene? If you work in construction, you know that it is used in,
So like torches.
yeah, I was looking for the word torch, to cut metal, you know, it produces really, really high temperature flames, okay? So the acetylene formula is C2H2. So how are we going to arrange it? 2 carbons should be in the center, right? And hydrogens should be in the periphery. You with me? So these are going to be the bonds between them. Now let's count how many valence electrons total we have in this molecule. Hydrogen, how many electrons does it have? 1. So we have 2 from hydrogen. How many valence electrons do we have from carbon? 4. 2 carbons means 8. So total 10, right? Does that make sense?
Yes.
Now, we got it so far? The calculations, 10. So each of these bonds, how many electrons does it take? 2. So how many bonds we have on this picture? 3. So how many electrons we already used for the bonds? 6. So 1, 2, 3, 4, 5, 6. Is hydrogen in its stable formation? Yes. What about carbon? No. But we still have 4 electrons left, right? So what if we added 1, 2, and 3, 4? Look at this. How many electrons? So imagine that we add these 4 electrons so that they form 2 more bonding pairs. How many electrons, quote unquote, belong to this carbon? 2 here, 2, 2, and 2. So 8 electrons. All 8 electrons are shared, but it's still 8. Does that make sense? Do you see what I'm doing here? Not really? What exactly is not clear?
Okay, so the hydrogen has 2, and 1 is from the carbon. And then
Hold on.
carbon
Go
has
ahead.
4.
Yes.
And so even he get 1 from the hydrogen, he has 6. And then you add 2 from where?
Slow down. In this image that I have here, how many electrons did I draw? 1, 2, 3, 4, 5, 6. How many electrons total do we have
10.
for all these 4 atoms? 10,
10.
right? So we used 6 electrons. We have 4 unused electrons. How we distribute these 4 unused electrons so that each carbon atom has an octet. Look at this carbon. How many electrons does it have now?
4.
4. How many does it need?
4.
4. We have 4 more, so we cannot give them to just one carbon. We cannot split them. So we have to make this 4 share. There you go. That makes sense? So we have 3 bonding pairs between 2 carbons, and bonding pair between carbon and hydrogen, and bonding pair between carbon and hydrogen. That's the formula of acetylene. Does that make sense? Excellent. How do we name the compounds? Covalent compounds. Pretty much the same way we named bicomponent ionic ones. The first element, the first nonmetal, named by the element name. Second nonmetal, first syllable, and "ide." Okay? The only difference is that you have to use prefixes. Okay? So you have to use prefix that shows which subscript appears at a certain atom. Let's take water and try to name water properly using this rule. So the first nonmetal is named by its element name. What's the name of the first element in the formula?
Hydrogen.
Hydrogen. What's the name of the second element?
Oxygen.
Oxygen. What's the first syllable?
H. I mean,
Syllable. OX. Yes, ox. So oxide. Hydrogen oxide. Any subscripts? Any subscript? To it hydrogen. Dihydrogen oxide. Does that make sense?
Yeah.
Dihydrogen oxide. Mono is usually omitted. Mono means one. So dihydrogen oxide. So CO2. Name it for me.
Carbon oxide.
Carbon dioxide, because there is 2 at oxygen.
Dioxide.
SO3.
Okay.
Sulfur trioxide.
Sulfur trioxide. Does that make sense? Technically speaking, molecule of methane, how can you name it? Molecule of methane, CH4. Carbon tetrahydride. Does that make sense? Because hydrogen, the first syllable is HYDR, hydride. And the prefix for 4 is tetra. Okay? So di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, deca for 10. Does that make sense?
I assume we have to know this for the test then.
Yes. Basically, well, you will see it on the test. You have to be able to name. You have to be able to go both ways. Does that make sense? For instance, I tell you, what is the proper formula for carbon disulfide? You have versions. Okay? So pick the one that says CS2. Carbon disulfide. Does that make sense? Now, as usual, on every test, you are allowed to use periodic table. I will not let you use the table with prefixes. Okay?
With
Like
what? Present?
table with these prefixes, I will not allow you to use this. So you need to know like di, tri, tetra, hexa, octa. Does that make sense?
Mm-hmm.
And so that's naming. So that's your naming. Nitrogen. What's going to be the name here? Nitrogen. Hmm? How many?
Right.
3.
Trichloride, yes. Nitrogen trichloride. Got it?
Yeah.
Now, what if I H2S? Dihydrogen sulfide. Perfect.
Dihydrogen.
Because 2 hydrogens, yes, but only one sulfur. Okay, not really a curveball. It may look like a curveball, but the rules are the rules.
So it's a dihydrogen.
Dihydrogen
Dioxide.
That makes sense?
Yeah.
This is actually hydrogen peroxide, but that's not the point. And you have to be able to do it the other way. So I give you you should be able to write the name based on the formula, and you should be able to write the write, quote unquote, write. It's a multiple choice, you're not writing anything. But I can ask you, CS2 is, and you have names. You know what I'm talking about?
Yeah.
Carbon sulfide, carbon disulfide, dicarbon sulfide, tell me, you know, whatever it is. Or I can tell you phosphorus pentachloride has the formula like, and you pick the right formula. Am I clear? So let's write the formula. Phosphorus pentachloride, what's going to be the formula?
Phosphorus what? P.
Pentachloride. So P Cl5. Okay. Diphosphorus pentaoxide.
P2.
P2.
What was the rest of the name?
Pentaoxide.
Penta.
O5.
5.
Wow.
Not as bad as it seems. Okay.
We
Huh?
just need to remember.
Yeah.
You do. You do need to remember. And there are a lot of things to remember
Yeah.
in life. Does that make sense?
Yeah.
Now, how can you tell if the compound is ionic or covalent? Generally speaking, if the first element is metal, the compound's ionic.
Is that one?
Ionic, yeah. If you would invite 3 chemists and ask them if the compounds that contain alkali or alkali earth metals are ionic or not, they will tell you, oh yeah, they are. Yeah, they absolutely are. If you will ask them the same question about some transitional elements, I don't know, vanadium, chromium, they will start arguing for hours whether they are ionic or they're closer to covalent. They will never come to the agreement. So for our intents and purposes, we're going to stick to the rule. If it's a metal, it's ionic.
Okay.
If the first element is non-metal, it's covalent. We good?
Yeah.
We clear? So with this comes the concept of electronegativity, one of my favorite concepts. We discussed it before, I believe, a little bit, and we're coming back to it. So electronegativity reflects how strongly a particular atom pulls the shared electrons towards itself. Does that make sense? Okay. Remember the example with shared Xbox. So imagine you have 2 twin brothers, identical twins. They are equally strong. Each of them can beat the crap out of another, okay? And they have 1 Xbox. So they're going to share it equally. Does that make sense? They're going to play the same number of times. They're going to make sure that the use of the Xbox is fair. It's equal. Now imagine you have 2 brothers that are of a different age. One who is older is much stronger, and it can beat the crap out of a younger brother. So the older brother can easily establish the rule when he plays Xbox 5 times a week and his younger brother only 2 times a week. Does that make sense? That's uneven sharing. You see what I'm saying? So electronegativity determines how unevenly the electrons are shared, and it's basically, it depends on the ability of the atom to attract electrons, okay? To attract electrons. Remember, we talked about the trends in periodic table, okay? Look at your periodic tables. How does so look at the periods, okay? First, so in the period, how does the number of protons in the nucleus change from left to right?
Increases.
It increases. So if you have more protons in the nucleus, positively charged subatomic particles, they will pull, that nucleus will pull electrons harder. Does that make sense? More positive charge, harder pull. So which element of the second period pulls electrons harder to itself? Fluorine or nitrogen? Fluorine. Fluorine, because it has more positive charges in the nucleus. It has what, 9, I think, yes? 9, yes. While nitrogen has only 7 protons in the nucleus. Does that make sense? How does the number of protons? Now, that's slightly different. Now, if you think about the number of protons from top to bottom, that situation becomes a little bit more complicated. Because while the number of proton increases, in general, what else increases?
Electron.
Number of electrons and number of electron energy levels. Does that make sense? How does the size of an atom changes from top to bottom? They become larger and larger and larger. Does that make sense? Now, as electrons become more and more distant, the attraction becomes less and less. Does that make sense? And in this case, the distance wins over the number of protons. So electronegativity increases from left to right in the period, meaning that what we just figured out, fluorine is going to be more electronegative than nitrogen, for instance. That makes sense? And it also increases as you go from bottom to top. From bottom to top. So look at the 6th A group. Which element is at the top of this group? Oxygen. So it is the most electronegative element in the 6th group. Does that make sense? We got it? Now, what is the most electronegative element of all? Look at periodic table. Forget about noble gases, they boring. Huh? Fluorine. Now, this is electronegativity of different elements in the periodic table. For your own benefit, what you should remember, few things. First, fluorine's number 1. Oxygen's number 2. Chlorine and nitrogen share the 3rd place. Does that make sense? And nobody cares about what's going on next because you can look up the electronegativity in the table. But knowing that fluorine is the most electronegative, that oxygen is 2nd, and nitrogen and chlorine are the 3rd ones, is really, really useful. Does that make sense?
Yes.
Second important thing, electronegativities of carbon and hydrogen are very close to each other. Carbon is slightly more electronegative, but they're very close. Why do we care about carbon so much? What kind of chemical compounds does carbon form? They start with O. Or, ga, organic. Organic compounds, compounds that make up the human body. And the two most abundant elements in human body are hydrogen and carbon, and they make a lot of bonds with each other. Okay, so knowing that these bonds are not polar, and we'll get to that, it's really important. So basically I kind of gave away what we're going to be talking about next. We're going to be talking about polar versus non-polar bonds. So imagine you have two elements, the same electronegativity. Like two hydrogens, two chlorines, two oxygens, doesn't matter. They pull electrons equally strong. Are they going to share electrons equally? Yeah. Because not one can win. Does that make sense? Now, if you take two atoms that have different electronegativity, the electrons will be shared unequally. For instance, in the pair H versus Cl, hydrogen versus chlorine, which element pulls electrons harder? Chlorine. So electrons will, quote-unquote, belong to chlorine a little bit more. Does that make sense to you? So, non-polar bond is when elements either have same electronegativity, okay, or very close to each other. So you see, for instance, hydrogen and silicon, they're very close to each other. So the bond between them is going to be non-polar. Chlorine and bromine have very close electronegativities. So the bond between them will be covalent non-polar. Are we clear? Now the polar bond is when electronegativity difference between two nonmetals that form the bond is moderate, and we'll get to the actual numbers in a bit. So for instance, here electronegativity is 0.5. That's considered already polar. Here is electronegativity. The electronegativity difference is 1. Now let me ask you this. Can two polar covalent bond have the different degree of polarity? You see what I'm trying? That's probably too confusing. Basically what I'm asking is, electrons here are shared unequally. Electrons here are shared unequally. In which bond that sharing is more unequal? The bottom one, right? Sulfur oxygen. So this bond is more polar than the bond between chlorine and oxygen. Does that make sense to you? You understand? So, as polar bond becomes more and more polar as the difference goes up, it may form a dipole. Now, what does that mean? Dipole. Let's break it down. Di means two. Pole means pole. Just pole. Like you have one pole and another pole. North pole and south pole, right? So, take carbon and oxygen. Which atom in this bond will pull electrons harder? Dude, oxygen. Look at the period. Look at the period in your the second period. Which
Oh, right.
oxygen will pull harder, right? As it pulls electrons, what charge do electrons have? Negative. So basically oxygen kind of pulls a little bit, a tad more negative charges towards itself. Does that make sense? Which makes that oxygen charged a tad more negatively. You follow me? It's not completely -1 as we see in ionic compounds. It's that a little bit. So X box is not completely in oxygen's possession, but oxygen definitely plays X box more than carbon. Does that make sense? To show that one atom that forms the bond has slight negative charge, we put Greek letter delta. It's written this way. That's delta. Like an egg with a hook on top of it. Does that make sense?
Almost like a D has a.
It's like it's like a letter D. Where do you think our letters came from?
That's easy.
Okay, does that make sense? It's letter delta. So, for instance, in the compounds, like if you have an organic compound which includes the bonds between carbon and oxygen, oxygen will pull electrons towards itself. Does that make sense? Now, why it's important? If you ever will study organic chemistry, the basis of all reactions, like the mechanisms of virtually all reactions in organic chemistry, are founded on the interactions between slightly positive and slightly negative atoms. Does that make sense? How do you think slightly positive and slightly negative charges interact? Positive and negative charges, what do? They attract. So it's called like positive, slightly positive atom can attack slightly negative atom. Like interact with it, it's called attack. Does that make sense? So it really determines the chemical properties of a lot of compounds. We good so far? So what about ionic bond? In ionic bond, electronegativity is really dramatic. It's considered ionic if the difference in electronegativity is more than 1.8. Okay? So for instance, in potassium chloride, the difference is 2.2. In cesium sulfate, the difference is 1.8. It's still pretty considerable electronegativity, and this is going to be an ionic compound. So to formalize whether we consider a compound ionic, covalent, covalent polar, or covalent non-polar, sorry, these are criteria here. If difference in electronegativity is 0.4 or below, that's nonpolar. If difference in electronegativity between 0.5 and 1.8, polar covalent. 1.8 and higher, ionic. Does that make sense? So, what's the electronegativity of carbon? 2.5. Hydrogen? 2.1. What's the difference? 0.4. So the bond between carbon and hydrogen, according to this, is what? Non-polar covalent. Okay? So equal sharing. Polar covalent non-equal sharing, forming a dipole. And in ionic, you have a separation of charges. Does that make sense? So here are some examples of the molecules. You know, for instance, in hydrogen atom, obviously it's polar, nonpolar covalent. In the molecule that consists of bromine and chlorine atoms, what's the name of that molecule, by the way? BrCl. How do you call the first one? Bromine chloride. That's it. Bromine chloride. Okay? Covalent nonpolar. In HBr, hydrogen bromide, the type of bond. Look at the differences. Covalent polar, right? And if we look at the bottom one, just for kicks, magnesium oxide, the difference is 2.3. That's ionic bond.
Ionic don't got non-polar or polar.
It's just ionic because there's, look at this, it's sort of, ionic bond is an example of sort of terminal polarity. In this case, you have plus and minus. It's as polar as it can be. There is no non-polar ionic. You know what I'm talking about? Ionic by definition is the polar bond. We clear? Now, we're going to talk a little bit, start talking about the shapes, how different molecules are shaped. This is methane. Okay? Typical structural formula, molecule of methane. CH4. You following me? From this picture, look only on the left picture. What is the shape of the molecule? It's probably, it looks like a cross, right?
Yeah.
What's the angle between these two bonds?
90 degrees.
90 degrees, perfect. Turns out that in reality, the shape of methane is tetrahedral. You know what tetrahedron is, right? Okay, so tetrahedron is a body in which each side is a triangle. It's called isosceles triangle. So basically, that, no offense, when I was a kid, we had half and half sold in cartons shaped like tetrahedral. It's like a so it's triangle at the bottom, and all other sides are triangles, perfect triangles. You know, all triangles with the all sides having equal length.
So it forms a pyramid.
Yeah, it's a pyramid.
Yeah.
It's a pyramid with the foundation triangle, but all sides are absolutely the same. It's a tetrahedron. Now, why? If you would measure the angle between two adjacent bonds in such tetrahedral arrangement, it's going to be 109 degrees, more than 90. Now let me ask this. Which subatomic particles form a bond? No. Bond, chemical bond, formed by which subatomic particles? Just talked about it. Bonding pair. What? Say what? No. Bonding pair. Bonding pair of what? What are these tiny little thingies that we drew as dots? Shared
Electrons.
electrons. Great. Electrons, what charge do they have?
Negative.
Negative. So each bond is basically two electrons both having negative charge, right? So one bond is negative, another bond is negative, third bond is negative. What negative charges do to each other?
Negative.
They repel each other, right? So the point of drawing the shape of the molecule is to put all the electron pairs as far from each other as you can. Does that make sense? So here the angle is 90 degrees. So two bonds are really close. If you can move them a little bit farther, they will repel less. And the overall energy of the molecule will decrease, which is always good. Does that make sense? The purpose is to maximize the angles. You can maximize them to a certain degree. Like here you have 4 bonds. You have positioned them in a certain way. So the angle will be maximum for each measured distance between 2 bonds. Does that make sense? Okay, think about 4 bonds as 4 people that hate each other. When you put them in the room, if you put them really, really close, the tension in the room will be almost tangible, right? So if you have a room and you want to arrange the chairs in the way so these people are as far from each other as possible in the space of that room. Does that make sense? That's basically the idea behind, organizing, trying to figure out the shape of the molecule. And the branch of chemistry that does it, the common pronunciation of VSEPR theory is Vesper. Vesper, just, easier, Vesper theory. So basically there are 2 main states. Electron groups are arranged as far apart from each other as possible around the central atom. That's number 1. Number 2, specific shape is determined by the number of atoms attached to the central. One more thing before we will chat a little bit more about different approaches to drawing the Vesper structure. We figured there are bonding pairs. What other electron pairs we encountered today? Anyone remembers?
The lone pair.
Lone pairs, very good. Lone pairs. So lone pairs will not form a bond, but they still exist. Does that make sense? Mm-hmm. And they will still repel, because those are still electrons. Mm-hmm. You got it? So let's take a look at how Vesper works for a molecule of CO2. Okay? So I have central atom of carbon. Carbon is attached by a double bond to one oxygen and a double bond to another. Now in this case, lone pairs do not really play a role, because lone pairs here are at the peripheral atoms, not at the central. So central atom, you have only bonding pairs. What would be the arrangement that will provide the maximum angles between these bonds? Straight line. Why? Imagine that you will try to do it this way. Here, the angle is like, 120. Does that make sense? Mm-hmm. So they will repel each other until they will acquire this shape. That's the linear molecule. Does that make sense? Now, in the last 4 minutes, we're not going to talk about 3 electron groups. I want to throw something else at you. we're going to try to draw the shape of the water molecule. First, let's do the electron dot formula. Okay, so that's oxygen. How many electrons are at hydrogens? Just one. So they share one, right? That makes sense? So how many bonding pairs?
2.
Two.
How many, what you might call it, lone pairs?
Pair.
Two.
Two. Now, here comes the bit of a tricky part. Let's play with the shape of the molecule, shall we? So we figured, remember that central atom has 2 bonding pairs and 2 lone pairs. And all these 4 pairs, they repel each other. Does that make sense?
Yeah.
They all repel each other. Sorry. So let's say we have oxygen, linear. Okay? Now, here you will have to turn on your imagination for a second. So imagine you have lone pairs sticking out like this. Basically forming a cross. What's going to be the angle?
Straight.
90 degrees.
90 degrees. Can you rearrange them a little bit? Remember methane? What if we will try to position them so this and this hydrogen, and this end, all these ends, all these pairs are directed towards the angles of the tetrahedron. Does that make sense? What if you will try to arrange them basically this way? You see what I'm saying? Does that make sense? What if you will try to arrange them like this? Is that understood? So I'm going to draw on this image. Forget that it's methane. So central atom is oxygen. This is hydrogen and this is hydrogen. This is lone pair. And this is lone pair. What's the angle between 2 hydrogens? About 109. In the real molecule, it's going to be, due to some other reasons, about 109.23 or something. But the point is, it's going to be more than 90%. Does that make sense? So, because the central atom has lone pairs, the shape will not be linear. That makes sense?
No. Sorry.
Okay, that's fine. So I'm going to try and show it myself. It's not going to be recorded on the screen, obviously. But, so, I am the molecule of the water molecule. Okay? Does that make sense? So oxygen, I can't produce the perfect cross. So the oxygen is somewhere here. Okay? Does that make sense? This is one hydrogen. This is another hydrogen in my legs. Those are lone pairs. So here I am forming the cross. What's the angle between the lone pair? These electrons? 90. 90. 90. 90. Does that make sense?
Yeah.
Can I change it a little bit?
Go down here.
Well, I can try. It's going to be something like that.
Oh, okay.
Okay? Does that make sense? So that angle is not 90 anymore.
No.
It's about 109. I mean, I cannot bend like this. I'm sorry. Okay? It's very unnatural, but so I try to push my arms back, and if I would be able to bend over here, that would be lovely, but I can't. So imagine that I'm bending here. So that angle is about 109. That angle is about 109. that angle is about 109, and that angle is about 109. Does that make sense? So, and I am bent over here, so I have oxygen here and hydrogens at an angle. So this is why water molecule isn't linear, it's shaped at an angle. Better? Good. So, your